Hello, everyone. We're starting some more of Chapter 3. Chapter 3 is kind of weird. We split it up kind of different. So this is graphs of parent functions, and there's 8 parent functions, and it's important to be able to know what these look like, be able to recognize them, recognize the shapes, etc. You don't need to memorize them for a quiz, mostly because a memorizing quiz is kind of silly when you're at home, but it is good to memorize. So first we have linear. And parent functions really just means that they're centered around 0, 0. That's what makes it a parent function. So f of x equals x is a general linear function, same as like y equals x, it's a line. And the idea is the parent function is centered at 0, 0 like that, and as soon as you move it around or change the slope, that's kind of changing the parent function to look different. So then we have quadratic, x squared. Again, this standard right side up parabola, and if you make it negative, if you move it around, it changes it. Cubic, f of x equals x cubed. Square root, square root of x. Yeah, the names aren't too hard to memorize at least, huh? Inverse variation, this is f of x equals 1 over x. Inverse square, 1 over x squared. And then absolute value of x, exponential growth is b to the x, okay? And we're assuming right now this is b is greater than 1, so it's exponential growth. Exponential decay is when b is less than 1, so this is going upwards versus going downwards. Okay, in general, just when you make a graph, what makes a good graph, things to consider. Axes are labeled appropriately with the scale shown. The window is chosen so that the characteristic shape of the graph. So as far as the shape, what I mean by that is, let's say you're looking at the inverse variation graph, and let's say your window only shows this. If that's all you see, you're really not getting a picture of what the graph looks like, right? You're only getting half of it. So that's what I mean by making sure the window shows the shape. You don't want to show just part of it. The intercepts and vertices are shown. So x and y intercepts where the graph crosses the x and y axes, and also the vertices. Vertices meaning like for x squared, for example, you probably wouldn't just show like this part, right? You'd probably want to show that point down there. That's what I'm talking about with vertices. Any endpoints are indicated as included, which would be like this, or excluded, which would be like this. Okay, a bracket or a parenthesis. We'll talk about this in a little bit. It's more like domain and range. And asymptotes are shown with dotted lines unless with the x or y axis, and then you can't really do that very well. Because there's kind of already a line there. Okay. Here's what we have. So for this first example, we have a graph of g of x equals x plus 25 minus 10. What's the domain and range of the function? So if you put this on, let's say Desmos, and let's graph, I'm typing over here on the side, y equals, let's see, gotta find the absolute value symbols, functions, no, where's absolute value? There it is. Sorry. I know it's fun to hear me talk to myself, not really. X plus 25. And on your graphing calculator is good too. I can't currently do that because my license expired with the online one. Not that you care, but so that's what it looks like. And we're like, okay, well, we got to move this. And on your graphing calculator, we can change the window. When we're back together, I'll show you how to do that. But if I zoom out a little bit, this is what it looks like. Okay, and this is the point -25, -10. Again, graphing calculator, don't worry about it yet. We will talk about that in person because it's so much easier to do it that way, and it just works better than like in a video like this. Okay, so what the graph looks like is the general shape of the absolute value function, but this is at -25, -10. And it does essentially that. I'm not worried about exactly where it intersects the y or x axis at this point. Domain and range. So domain is the x values. So going from like left to right, what values work, and it looks like anything goes, right? All the x values, you can plug any value into that equation and you'll get some number. So domain is -infinity to infinity. And we always have these parentheses because you can't include infinity because it's not really a value. Range is the y values, and it's hard to recreate this in a video, but I usually think like starting at like -infinity, like basically where does the graph start? You're moving up, you're moving up, you're moving up. Oh, it looks like it starts there, which is a y value of -10. And there's a point there, so it's included. And then you kind of move your way up and you're like, well, where does it stop? Well, it doesn't, I mean, it stops when we drew it because we can't draw a line infinitely, but there's arrows. It's going to keep going forever. So it goes until infinity, okay? And that's open because you can't include infinity. So now let's talk about this. So our parent function, definitely absolute value, right? The general form of this function looks like y equals absolute value of x minus h plus k. If you recall from mostly last year in advanced algebra, I think, you ended up with h's and k's all over the place. And basically, h's and k's are a vertex, where h is the x coordinate and k is the y coordinate. And in this case, our vertex in this case was -25, looking here, -25, -10. And so basically the way that works then is we can think of x plus 25 minus 10 as x minus a -25 minus 10, okay? And basically what happened is this graph was shifted. So if you think of where the parent would be right here, centered at 0, 0. So the parent graph was shifted 25 left and 10 down. And again, this is from the parent graph. So you start with the parent graph, what happened, 25 left and 10 units down. Now let's look at square root of x minus 8 plus 5. Again, we'll deal with graphing calculator, not right now. So y equals square root of x minus 8 plus 5. Okay, so if we kind of move this around a little bit, looks kind of, it's like floating there, isn't it? It's kind of bizarre. But basically that's the point 8, 5. Okay, so it's the shape of the square root graph, except that it's moved. Okay, so looks like, let's see, this is 8, 5, and it does that. Okay, so the domain, going left to right, where does it start? Starting on the left, it doesn't start until 8, right? So an 8's included because there's a point, and it's going to go on forever. So that's what square root graphs and lots of graphs do. Range, once again, I'm going to start at the bottom. Do I see the function? Do I see the curve? Nope, 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 nope. There it is. The y value is 5. It's included because it's a point, and then you're going to keep going. Just going to keep going. It's not going to go very fast. It kind of looks like it's flattening, but it's still going to go to infinity. Okay? And then our parent It's pretty easy to see the parent when you have an equation, I think, because what do we see? We see a square root. So the parent is y equals square root of x. The general form, y equals square root of x minus h, so you subtract your h, plus k. And so in this case, it's not a vertex because only one point is coming off of it. So we're going to call it just an endpoint, and it's 8, 5. And so that's like our hk, okay? So it was x minus 8 plus 5 instead of x minus h plus k. And basically what happened is the function was shifted 8 to the right and 5 up from our parent, because our parent would have been there, and we just shifted it. Make sure you practice these problems. Know that looking at number 2, the set of all real numbers just means where we have negative infinity to infinity. A line of symmetry is when if you reflect the graph over itself, or if you make it a mirror image, basically it's the same on each side of a line of symmetry. For number 4, graph this. I don't expect you to know what it looks like, but graph this and think about that. Okay? Yep, graph these, you'll be just fine. The only thing I guess I want to talk about is asymptotes for a second, just in general. If you think about which ones have asymptotes, if we go back to the top here, sorry if I'm making anybody dizzy, just like moving this around. The only ones that have asymptotes are inverse variation, inverse square, and exponential growth. And if you'll notice, these are the ones that don't have intercepts either. They just have asymptotes. Okay, so inverse variation. So y equals 1 over x squared. This one looks like this. And basically the asymptotes are what the functions are approaching as they go to infinity, either domain or range, but basically as they go to, as x or y goes to infinity. So this is approaching the y-axis there. It's getting infinitely close to the y-axis, infinitely close to the x-axis, same on the other side. So the asymptotes for this one are going to be y equals 0, which is the x-axis, and x equals 0, which is the y-axis. For y equals 1 over x, sorry for my messy notes here, which looks like this. It's the same asymptotes. You know, it's like it's up here and down here. They're in different spots, but the x-axis is still being approached and the y-axis is being approached. So this is still x equals 0 and y equals 0 for our asymptotes. And keep in mind y and f of x are the same thing, right? Doesn't matter. It's just different notation. Y equals b to the x. It looks like this, and basically this is going on forever there, but as x goes to negative infinity, we're approaching the x-axis, right? Getting close to 0, and the x-axis is y equals 0, so that's the asymptote. Okay, and basically what happens is, just like a vertex or an endpoint would shift around, the asymptotes do as well.